Welcome to this educational video about statistics. Today, we'll explore how statistics differs from other scientific disciplines by focusing on macro-level patterns rather than micro-level rules or laws. Let's begin by distinguishing between micro and macro approaches to understanding the world. Many sciences like physics and chemistry focus on finding fundamental micro-level laws that govern individual particles, objects, or events. Statistics, on the other hand, operates at the macro level, studying aggregate patterns, variability, and uncertainty across large populations or datasets. Let's examine the key differences in what these approaches study. In physics, we might have Newton's second law, which tells us exactly how a single object accelerates when a force is applied. This is a deterministic micro-level law. The formula F equals m times a precisely describes how one object behaves under ideal conditions. In statistics, however, we're more interested in population-level questions like, what's the average height of adults in a country? Or how do test scores distribute across students? We observe summaries like means, proportions, and distributions rather than the exact mechanism governing each individual. A key difference is the role of randomness and variability. Deterministic sciences often assume idealized noise-free conditions. In a perfect vacuum, with no air resistance, an object falls exactly according to gravitational equations. But real-world phenomena, whether biological, social, or economic, exhibit inherent variability. Take the stock market. Even if underlying economic mechanisms exist, countless factors like investor psychology, global events, and regulatory changes introduce randomness that can't be precisely modeled at the individual level. Statistics acknowledges and quantifies this variability, helping us distinguish meaningful signals from random noise. Let's explore another important distinction: inference versus mechanism. Mechanistic sciences explain how or why phenomena occur at a granular level. For example, biochemistry explains exactly how enzymes and substrates bind together in chemical reactions. Statistics, however, asks, what can we say with confidence about the whole? It's concerned with making reliable inferences about populations from limited samples. Using tools like confidence intervals, hypothesis tests, and regression models, statistics helps us estimate population parameters, test differences between groups, and forecast trends even when we can't observe every individual. One of the most fascinating aspects of statistics is how macro-level patterns emerge even when individual behaviors seem random. The law of large numbers and the central limit theorem show that aggregates behave predictably even if individuals do not. Consider coin flips. A single flip is unpredictable, heads or tails, but if we flip a coin 10,000 times, the proportion of heads will almost certainly be very close to 50%. Let's see this in a simulation. As we increase the number of coin flips, watch how the proportion of heads converges toward 0.5 or 50%. In real-world scenarios, we often need to make decisions without complete information. Statistics provides tools that guide decision-making under uncertainty. Policymakers use unemployment rates and economic indicators to make fiscal decisions. Businesses analyze consumer data to predict market trends. Healthcare providers rely on clinical trial results to select treatments. Through confidence intervals, hypothesis tests, and predictive models, statistics helps quantify uncertainty and make evidence-based decisions even when we can't observe every micro detail. Modern systems involve incredible complexity and high dimensionality. Social networks, genomics, climate systems, and financial markets involve so many interacting parts that micro-level modeling quickly becomes intractable. Statistics and data science use dimension reduction, clustering, and regression methods to extract essential macro patterns from complex data. Even when we can't model every interaction, statistical approaches can reveal underlying structures and relationships. It's important to note that statistical and mechanistic approaches often complement each other. In fields like epidemiology or ecology, mechanistic differential equation models coexist with statistical models. Hybrid approaches like statistical physics and stochastic simulation blend micro-rules with statistical inference for understanding aggregate behavior. The most comprehensive understanding often comes from using both approaches together. To summarize what we've learned about statistics, statistics is the science of learning from data at scale. It embraces randomness, quantifies uncertainty, and identifies reliable macro-level patterns. While it may not reveal every micromechanism, It tells us what we can know and how well we know it about entire populations or complex systems. By focusing on macro-level patterns rather than micro-level rules, statistics provides a powerful lens for understanding our complex world.